Okay, now how do we differentiate these new inverse trig functions? That is to say, how do I define the slope of this graph at any point? Or this one, or this one. I mean, here looks like its slope is 45 degrees. Up here it looks like it's infinite, and down here it looks like it's infinite. This looks more or less the same, except it's a negative slope. And this one approaches zero slope at the edges. It's really tricky to try to define this. What we're going to do is use a trick. It's a mathematical trick. dy dx is 1 over dx dy, provided it's not 0. Why is that important? Because otherwise we're dividing by 0 and it doesn't make sense. So, if this seems a little odd, think about straight lines. Now this is not much of a proof. Okay, this really isn't much of a proof, but it kind of gives an example. If I start with this linear function, its gradient is 1/3. If I get the inverse function and rearrange it, I get a gradient of 3. So the gradients of each of them are reciprocals. The gradient of one is equal to 1 over the gradient of the other. Now we're going to extend that to the arcsine, arccos and arctan functions. So, if I make y arcsine x, or if you prefer sine to the -1 of x, doesn't matter. So we know that y is going to be between negative pi on 2 and pi on 2. We also know that x is between -1 and 1. And we also know that x is equal to the sine of y. Think about that. If y is the arcsine of x, then x is the sine of y. Okay. Well, dx dy, the derivative of this with respect to y, is cos y. So dy dx is 1 over cos y, which is sec y, but that doesn't quite help me. What I want to do is get back to sine. Well, if I've got a cos and I want a sine, I use my old friend, the Pythagorean relationship, Pythagorean identity, which says that cos y is the square root of 1 minus sine squared y. But actually, it's plus or minus. I don't know which. But sine squared y is just x squared. That was a clever trick, wasn't it? X is sine y, so sine squared y is x squared. Now, here's the clever bit. Negative pi on 2 and pi on 2 are my bounds for y. And if that's the case, then I know that cos is positive. Let me say that again. Because y is between negative pi on 2 and pi on 2, I know that cos is positive. So that means cos is only the positive square root of 1 minus x squared. That was heavy going. You probably never had an argument like that before. If you need to, go back and watch it again, or get your textbook out and have a read through yourself. The conclusion is that the derivative of arcsine of x, is 1 over the square root of 1 minus x squared. You would probably never have worked out how to come up with that function just by looking at this graph. You can do similar things for arccos and arctan. I'm not going to show them to you, and nor is your textbook. In fact, the textbook says you get to show them in the next exercise. Derivative of arcsine, which we just looked at, was 1 over the square root of 1 minus x squared. Derivative of arccos is basically the same, but with -1. Now that makes sense. When you looked at those graphs, the sine graph went that way positive and the cos graph went that way negative. Actually, maybe it's better if I draw them for you. The sine graph went like this, and the cos graph went like that. So the sine graph's gradient is positive all the way, and the cos graph's gradient is negative all the way. The derivative of arctan is 1 over 1 plus x squared. Now, by the way, don't panic about how funny these look and how hard it's going to be to remember them, because on your formula sheet they are here. Derivative of arcsin, derivative of arccos, and derivative of arctan. Now they actually have an adjustment here, divided by a, which we'll come to later. It's the next little bit after I do some examples for you. But you don't have to try desperately to remember the exact forms of these derivatives. They are on the formula sheet. So, this is just what we said before. Arcsin is positive because the gradient's always increasing. Derivative of arccos is always negative. The gradient's always decreasing. The derivative of arctan is always positive. Now, we noted that when we looked at the graph. Remember, the graph of arctan looks like that. So the gradient is positive but gets close to 0, but always positive. Also notice that these derivatives for arcsin and arccos are not defined when x is plus or minus 1, because you would be dividing by 0. Now again, remember those graphs. At those points, that gradient was pretty much infinite. You can't actually give a value to it. There's another way to explain this too. It has to do with the definition of derivative. Remember from first principles, the derivative is, by definition, that limit as h approaches 0. What you actually have to do is look from both the left and the right and make them match. And if they match, then you say it's differentiable and that's its value. But these functions don't have a value to the left or right, so they're not differentiable at that point. So the derivative just does not exist at x equals plus or minus 1.